We have to do one more section on Taylor series, and this is called working with Taylor series, and we have actually done something similar in 6.2. The difference here is that we have more series now. And so let's start with the table that I also gave you last time of the various functions that we have and the series that we have. So here is f of x. And the first one we discussed already in 6.1 or 6.2 was 1 minus x, the geometric series. And we had this formula for that. The series for this. And so that's the Taylor series or Maclaurin series, because everything that I'm doing here is centered at 0. I could work with other things, but for in this section, I'm just going to work with center 0. Okay, and then we have the radius of convergence. That's of course very important, because what it tells us that the function and the Taylor series can only be considered to be the same when you have where you're inside the interval of convergence. Okay, that's the first one that we did in the first week ago. But now from last time we have learned about 3 more, and perhaps more, but these are the ones that I'm going to look at. First of all, we have the exponential series, EX. And the pattern here is that you have the factor, you have a power, and in the bottom you get the factorial of that exponent. And this is also true for the first 2 terms, because 0 factorial is 1 and 1 factorial is 1. And here we are lucky that the radius of convergence is infinity. We have the sine and the cosine. Let's start with the cosine of x. The only thing you have to remember, it's very similar as the EX, except, first of all, that in the cosine you only have even terms. So you get 1 minus x squared over 2 factorial, which is of course just 2, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and so on. Again, the radius of convergence is infinity. And the sign is almost the same, except that this time we have the even powers. So we have x minus x, but I'm saying the odd powers, x cubed over 3 factorial, plus x5 over 5 factorial, minus x to the 7 over 6 factorial, etc. And again, radius of convergence infinity. Okay, so these are the 4 functions that we're going to work with in today's lecture. Before I start, I want to point out that some of the properties that you know of these functions here, we know properties of these functions, you can see easily also reflected in their Taylor series. For instance, this series, if we take the derivative of it, it's equal to itself. So I invite you, take the derivative of the series here, and you'll see you get exactly the same series back. Okay, we know this happens. What about cosine x? We know this property, well, you might have forgotten this, but it's something you learned in trigonometry, that the cosine of an angle is the same as the cosine of the negative of the angle. And now you can see this very easily in the series, because if you replace x by negative x, you're taking even power, so the negative sign doesn't play a role. Okay? And for the sine, we have that sine of x, sine of negative x is negative sine of x, and that comes from the fact now that we have odd power, so we have a negative sign coming out. Okay, but that's not what we're talking about today, so I'm going to put this away. It's not what we want to do. We have several things we can do with this series. We have, as before, so it's nothing is new here. So it's basically really a repeat of what 6.2, but with more series. Let's remind us what we can do. Well, we first have the substitution that we can do. Substitution. But I'm going to only, since I want to stay at the center 0, the only thing we really can do is replacing x by, let's say, 8 times x to the power n. So a multiple of a power of n, and it has to be a positive power. I'll give examples. That's the first thing. The other thing we can do is we can take the derivative. And a derivative of a series is just done term by term using the power rule. We can take the antiderivative. That is the same. But then, of course, the power rule for antiderivative. And finally, we can also add, which is not so interesting, but even what is interesting, or we can multiply them. Dividing is a different issue, and I'm not going to talk about that. Okay, so let's see each of these four at work, and let's start with this one here. I want to do the cosine of x cubed. Okay. So here by constant, the a here, the coefficient is just 1. Often it is, but so, okay. So how do you do this? Well, so let's write down one more time the series for cosine. So it's up there, right? So the cosine, but instead of writing x, I'm writing parentheses, and inside would be whatever x is, right? So we get this, right? Parentheses to the power 4 over 4 factorial minus parentheses to the power 6 over 6 factorial, dot, dot, dot. And now in there we plug in x cubed. I'm doing this so that you see exactly where these powers that I'm going to get come from, because you have to then take into account that if you take a power of a power, you multiply in the exponent. So you get 1 minus x to the 6 over 2 factorial plus x to the 12, 3 times 4 over 4 factorial minus x to the 18 over 6 factorial, dot, dot, dot. Of course, the bottom is just constant, nothing changes. Okay, and that's a new series. And what about radius of convergence? Well, the original one has radius of convergence. That cannot change. So in other words, the only time when we have to pay attention to the radius of convergence is in the very first case here. But other than that, whatever we do with it, we're never going to violate anything. We change the radius of convergence. Okay, that was so this was substitution. Let's do derivatives. And okay, I can do it for the original ones, but the whole point is that I'm going to build new functions, and then I can do these operations with these new functions. So I'm going to use my cosine x cubed, and I'm going to take the derivative of this. Derivative of cosine x cubed. If I take derivative of the left-hand side, I can take derivative of the right-hand side. So I'm going to take derivative of this series there. Okay, and what is this? Well, that's very simple, right? Derivative of 1 is 0. We'll write it, although it shouldn't. No point in it really. Derivative of this thing. Now be careful. This is not a power. This is not a quotient rule or anything, because that is just a 1 over 2 factorial, whatever factorial we have. That's just a constant, right? So this is 6x to the 5th, the power rule for derivatives over 2 factorial. Plus, and here we get the exponent comes down and lower the exponent, and you just divide by the coefficient that you had. 18 over 6 factorial, etc. And that's it. But again, the radius of convergence does not change with this operation. So we get a new series here. Now, you could say, yeah, but I know what the derivative of this thing is, because by the chain rule, let's see, right? The derivative of cosine is negative sine, plug in the inside function, and then multiply with the derivative of the inside function. So what I'm saying is, if everything is correct, then this series should be equal to that. And now this is something you can verify, because now you have sine of x, and you plug in sine x cubed, you have a minus sign, and then you multiply with 3x squared. I haven't talked about multiplication, but later on you could double check here that both sides give indeed the same series. Okay, let's go to an antiderivative. This is more interesting. And I'm going to again use my cosine x cubed here. Let me box it a little bit. So this is the series that I have, right? This is, as you want, a new series. And I can now antiderive, so I can look at this guy. Why I say this is much more interesting, because the antiderivative that I just wrote down, it exists. We know every continuous function has an antiderivative, but this is one that we cannot write down. It's not that we're stupid, it's just impossible. There are no formulas for this antiderivative. This is because the inside x cubed there, if there would be an extra x squared running around, then we could consider substitution, but nothing else we can do. There's no double product formula or anything like that will work here. Trust me. But it's now very easy to write down a series for it, because you just take the series you have, of course, an x cubed, and you integrate. The derivative of 1 is x. The antiderivative of x to the 6, you add 1 to the exponent and divide by the exponent, and of course we still have that coefficient in the bottom. That's just a coefficient, so again, that is allowed. Plus, now, this would be add 1 to the exponent, divided by the exponent, 4 factorial, minus x to the 19 over 19 times 6 factorial. And that's a minus sign there in case that has been lost. Okay? Plus dot, 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 of course. And again, the radius of convergence does not change. And this is, as I said, more interesting because we don't know how this thing would look like. And so, for instance, if this is an antiderivative, but part of this is also, of course, I could now also consider, for instance, an actual derivative. I mean, a definite integral. And what would that be? Well, the difference would be now that we just have the fundamental theorem of calculus, we plug in the endpoints. So we have this series here in which we plug in 0 and 1. And we can do this because the radius of convergence is infinity, so it doesn't matter what we plug in. So if I do this, we get plug in 1, I get 1 minus 1 over 6 times 2 factorial, plus 1 over 13 times 4 factorial, minus 1 over 19 times 6 factorial, dot, 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 minus, and then I plug in 0, but you see that all the terms are 0 here. Okay, so you're done. So this tells me that I have actually a series here. This series calculates for me the value of this integral. And very often, when, especially in applications, in engineering applications or whatnot, you need only an approximation of this integral, and this series, if you go enough terms, and depending a little bit on the type of series, you get a good approximation. I think here, after 4 or 5 terms, you do already get a really good approximation. But upon to do it, we cannot really verify this because we don't have any other way of doing this. This is the way that we have to do it. Okay. Yeah, but one thing I should have mentioned here, when we antiderive, there's of course also plus a constant here. And that constant sometimes, since we don't have a formula for the integral, we cannot figure out what the constant is that we want. It depends on what we want. Okay, so let me give you, remind you of one thing that we did. So the arctangent. So okay, no, let me do this. Sorry, let me do this. This is an example I did already, but I'm going to do it again, and hopefully you well. Okay, let me do this one first. So give a formula for the arctangent x cubed dx. It's almost something that I did. Now, this you might panic because you say, I don't have a series for arctangent, and you're right. We haven't written it down. In the book, actually, they wrote down, but why didn't we write down? Because we can figure it out. But I don't know whether, when I say we can figure it out, I really mean perhaps we. I need to help you with here. So I would break this down and say, step 1, find a series for 1 over 1 plus x squared. Step 2, find a series for arctangent of x. Now, you might say, I don't see what step 2 has to do with step 2, 3, or whatever, but they have this to do with each other. Bear with me, okay? Then, find a series for the antiderivative arctangent of x dx. And step 4, I should warn you, in the book they combine step 3 and 4 in one single step, but I like to put it as 2 different separate steps in a slightly different way. It's a different way for the series no, sorry. Sorry, yeah, no, sorry. I got confused myself now. Sorry. Step 3 is I have to first plug in x cubed, then antiderive. Okay, sorry. So I meant to say, let me get rid of this here. Wait, sorry. Fine. This one, sorry, I forgot that there's an x cubed there. And then lastly, now I can antiderive this thing. Okay. So why am I breaking down in these steps? Well, the first step is perhaps something you have to think a little bit about it, but it comes from, remember, we have these 4 tricks that we can play onto these 4 functions. Now, it's clear that the function that we should work with is the first one, and that's why we had already discussed this example, because we had this already. So what I'm going to do is write up again 1 over 1 minus x, and I do this funny thing where I, instead of x, write just parentheses, right? That's how this was, right? And now in what I have to do, I have to replace what, let's think about it. You say x squared, but then you got 1 over 1 minus x squared. So what I really have to plug in, I hope everybody sees this, is minus x squared. So I get a minus x squared here, a minus x squared, a minus x squared. Now, I do have to also take into account this condition, x less than 1. So in this case, sorry, if you want, it is the absolute value of whatever you plug in, the parentheses has to be less than 1, and so I'm plugging in x minus x squared here. Okay, so let's work it out. This is 1 minus x squared, then I'm cubing, so the power, squaring, the power goes away, x to the 4th minus x to the 6th plus x to the 8th, and then we'll get a minus again, and this is 4 x squared less than 1, which is the same as x less than 1. Absolute values go to, the minus sign of course disappears because of absolute value. Okay, so this is what I meant. So we have now 1 plus x squared, we have now a series for 1 plus x squared. And that is what step 1 asked. Now step 2 is perhaps the one that is the biggest leap. How do you go from arctangent to 1 plus x squared? Now, once you have seen this, you know that is because antideriving, right? The antiderivative of 1 plus 1 of x squared is arctangent. Okay, so what we do is we take the antiderivative of 1 plus x squared dx. We know that this is arctangent of x. So we do this under, so let me write it on the other side. So on the one hand, we know that this is arctangent of x. And on the other hand, we know it's gotten by antideriving this. So x minus x. You add 1 to the exponent, divide by it. 5 minus x to the 7 over 7, dot, dot, dot. And this is for x less than 1. The same condition, because integration doesn't change. Plus c. And the plus c is the part here that I was trying to say. Sometimes we can figure out what c is, because we want arctangent. That is the one that we are going for. And we know this arctangent. What is this function? And so what is c? To find out c, we need to substitute x equals 0. It will always be x equals 0 because that's the center. In general, it's the center, but as we said from the beginning, we are working with Taylor series centered at 0, which the book calls Maclaurin series. Okay, so plug in 0. We know that the arctangent of 0 is 0. Look that up if you don't remember anymore what it is. And that one on the one hand, and on the other hand, here, if I plug in 0, the only thing that it gets you survive is c, because everything else has a power of x. So the whole thing actually tells you c was 0. So we have, let me remind you, we have 1 plus x. So, sorry, no. So the arctangent of x is equal to x minus x cubed over 3 plus x5 over 5 minus x7 over 7, etc. And this is still for x less than 1. Okay, so all right. Now, what's the last step? No, the next step, sorry. Now we have to find for x tangent x cubed. Again, this is very simple. We replace x by x cubed. I'm going to do this now quickly. X cubed. X cubed cubed, that's x to the 9, because we multiply exponents. X cubed to the power 5 is x to the 15th over 5. Make sure that you understand why these powers, right, and nothing else. This is for x cubed less than 1. But again, if I solve this equation, it doesn't change. It could, right? Because if I put, instead of x cubed, I could have put in, say, 3x cubed, and then it would change. Okay. So this is step 3 now. So this was step 2. Hope you're following. And then finally, find a series for this guy. Now I'm done, right? So I have to antiderive whatever it is that I have. I'm doing antiderivative here. I get x to the 4th over 4 minus x to the 10th. Add 1 to the exponent and divide by this exponent. Plus x to the 16th, 15 times 5. Etc. I'm not going to write that down. And again, radius conversion doesn't change. And so this is the series that we were looking for. But you see, this is by no means obvious anymore how to get the series. And even what the numbers in the bottom are, we can trace it back. If we go back all the way, we can figure out what the next one is. But just looking at the pattern is not so obvious anymore. Okay, that's in one example. I want to do, the one thing I have not done yet is what about multiplication? So let's start with a simple example. Let's say we want to do x cubed times ex squared. We find a series for this guy. Now, I hope you see that you have to break this down, because we need first a series for this guy. So step one would be, let's get a series for ex squared. Well, how do we do this? We have e to the power x is 1 plus 1 x plus x squared over 2 factorial plus x cubed over 3 factorial plus, again, right, this is, I get this from my table here, right? But instead of x, I write parentheses, okay? And in there, we plug in x squared. I'm doing it one more time that you see what happens. I plug in x squared here, x squared, and what do I get? 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus dot dot dot. Now, what is the range of convergence? We discussed this. For these guys, it's always infinity. Okay, that's step one. We have now a series for ex squared. Now, what is the series for x cubed times ex squared? So we have to multiply. And we discussed multiplication of series last time, so I'm going to do this here very quickly. It is especially simple here because it's only one, it's a single power here, right? So you just have to distribute here. In general, of course, this distribution could be quite a lot of work, and then I would say only so many terms you have to give. So here we get x cubed. Now, multiplying, remember, is adding exponents, right? This is x to the 5th and not x to the 6th, plus x to the 7th over 2 factorial, plus x to the 9th over 3 factorial, plus dot dot dot. Okay. Well, that's it. I'll do one more example. So the example is, let's do, for instance, sine x squared times ex to the 3rd. Okay, now we need a series for the one factor and for the other one. So we have to step one would be get a series for sine x squared. Or we could do the other one first, doesn't matter. So remember, the sine is, well, remember, this is what you have to look at the tables, but it's good to actually try to memorize them. Although you can look it up, it makes your life much easier if you know the things, right? You don't have to keep looking up. So it's the odd powers, so we get x minus x cubed over 3 factorial. Then we get this plus sign and the 5th power over 5 factorial. And then we get, I'm going to do 3, well, let's do 4. So x to the 7th over 7 factorial plus dot dot dot. Okay, so in there we plug in x squared. So we have an x squared, x squared, x squared, x squared, and x squared. So this is x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, etc. Okay, that's sine x squared. We also need one for ex cubed. So ex cubed, well, that was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. Okay, you see I always take 4 terms here. So now I plug in x cubed. I will be more precise how many terms you would have to go. But in general, let's take a rule. The first 4 non-zero terms, okay? I don't mean, see, if I say all the terms up to degree 4, this is ridiculous, of course. Here there's only 1. Okay, so always we'll say the first non-zero so many. Sometimes I say that, sometimes I say up to a degree, depending on what it is. So read the question always carefully, because you don't want to do too much either. 1 plus x cubed plus, okay, now we are substituting, so we're multiplying x to the 6th 2 factorial plus x to the 9th 3 factorial plus dot dot dot. And now we have to multiply, so step 3. This is, of course, where it gets a little bit messy. We have to do sine x squared times ex cubed. This means, okay, we have this, let's try to get our series. So we have to do x squared minus x to the 6th 3 factorial plus x to the 10 over 5 factorial minus x 14 divided by 7 factorial. Okay, so and then we multiply this with the other term, 1 plus x cubed plus x to the 6th. Give me a sec. Sorry about that. So x to the 6 over 2 factorial plus x to the 9th over 3 factorial. And then let's say I want to go up to degree 6. Up to degree 6. I will tell you always up to what degree or up to how many non-zero terms. Okay, so last time I made a table, so perhaps let's do this one more time here. So the various powers that we can get. 1x, x squared, x cubed, x4, x5, x6 here. Okay, so remember what I'm doing here is finding the coefficients in this product. And so what I do is I start, and let's say with the left one, I take x squared. Well, I look at 1. Can I make power 1 here? But since I start already with x squared, that's not going to be possible. So I'm going to have 0 here, and the same for x. So the first term that I can get is square. And I can do this by combining this guy with this x, which gives me coefficient 1, and that will be the only one, right? So that's clear. What x cubed? I cannot make an x cubed because this x squared already, with the x cubed will be given an x to the 5th, so nothing there. So that will be a 0. I think I'm going to go up to degree 9. Let's go up to degree 9 here. It might sound a lot, but as you see, most of these things are going to be 0. X to the 8th, x to the 9th. Okay, x to the 4th. Is there any way that I can combine this x squared with an x to the 4th? No, and x to this guy definitely not, because it's even higher, so nothing. X to the 5th. Now you have a combination. Let me show you. This is with the x squared I can make an x cubed. So that's what gives me a 1. But then the next term is already too high, so I can stop. Okay, what about x to the 6th? Okay, let's do x to the 6th. So with the x squared, there's nothing I can combine here because I'm never going to get the 6th power. And what about with this x squared? But be careful, this one actually now does contribute because I can mix it with, match it, sorry, with that one. And so I get minus 1 over 3 factorial. That's 1/6 here. I'm going to write what the factorial is. Okay, and then the next one is 10 power is too high. Okay. What about the 7th power? Well, with the x squared, I need an x to the 5th, which I don't have. With the x to the 6th, I need an x that I don't have, and this is too high. So this is going to be, again, nothing. So what about the 8th power? Okay, with the x squared, I can combine it with the 6th power here. And this would be coefficient, a 1 there and a 1 over 2 there, so 1/2. Okay. What about the 6th power here, this guy? Yes, that would work if there's a square here, but there isn't. So that's it, because then this one is again too high. And then finally the 9th power. Let's do this in a bit different color if you can still follow. The 9th power, can I combine the x squared with something? Nope, nothing there to combine it with. What about the x to the 6th? Yes, I can combine it with here. So it is minus 1 over 6, 3 factorial. Okay, and then of course this is too high again. Okay. And so you could keep going here. Let's stop now and let's see what we have. Okay, so the only ones that are non-zero are, so this is equal to 0, 0. Then we have 1 times x squared, so x squared, 0, 0. Then we have an x to the 5th with the coefficient 1. We have a minus 1 over 6 x to the 6th. That's nothing. We have a half x to the 8, right? This is this coefficient. And then finally this one is minus 1/6 x to the 9th, and so on. And you see this pattern is already much more erratic, and it's very hard to see what actually the pattern would be. But there is one, and there's a series. okay? So this is the type of questions that we are looking at here, and I'm going to assign some of the homework problems on this thing, and then, but when it comes to a quiz, and I will, next time we will go for a quiz here, what I will do then, I promise you, is that, for instance, if I would ask you something like this question here, I will break it down for you in steps, okay? So that each step you know what to do. And now, of course, if you don't know what to do in the first step, you're stuck in the next step. So sometimes I even might tell you, okay, in the first step you will find this series, but show me how you find this series. Remember, in this new modality that we're working, the actual results, the actual solutions are less important than the way that we get to them. Okay, so I might give you already, okay, this is the answer, but how do you get to this answer? Via these various steps. Okay, I'll give you a review of this next time for the quiz, then that will be on this kind of stuff. Okay, so that's everything for today then.